A pressure vessel does not fail because one equation stopped working. It fails because the real operating condition was never placed inside the equation. That distinction matters. You can calculate the shell thickness correctly, select a permitted material, obtain an acceptable weld joint efficiency, pass hydrotest, and still deliver equipment that is vulnerable in service. The calculations may be correct while the design basis is incomplete. The fabrication may be compliant while the material is wrong for the process environment. The vessel may withstand internal pressure while remaining dangerously weak under vacuum. The relief valve may be correctly sized for one scenario, while the actual governing overpressure case was never identified. Pressure vessel engineering is not a shell thickness exercise. It is the disciplined construction of an entire pressure integrity system. When you work with pressure vessel design rules, the first mistake you must avoid is treating the code as a design handbook. The rules establish mandatory requirements, specific prohibitions, accepted construction methods, and minimum boundaries for safe construction, but they do not know your process, corrosion mechanisms, shutdown practices, operating culture, maintenance limitations, or future plant modifications. The code gives you a floor. Your service may demand more. Engineering judgment fills the space between written rules and physical reality, but engineering judgment can never be used to override a mandatory requirement. It must remain consistent with the philosophy of pressure integrity. Your first serious question is not, what thickness is required? Your first question is, what exactly am I designing? Where does the pressure vessel boundary begin? Where does it terminate? Which nozzle connection belongs to the vessel, and where does piping responsibility start? Which covers, closures, attachments, instrument fittings, and proprietary components remain within the pressure boundary? Which local regulations or project requirements extend beyond the nominal construction scope? When scope is unclear, responsibility becomes unclear. Once responsibility becomes unclear, calculations, inspection, certification, and documentation begin falling between disciplines. Resolve the boundary before you calculate the metal. Next, define the complete design envelope. Normal operating pressure is not automatically design pressure. Normal operating temperature is not automatically design temperature. A familiar corrosion allowance is not automatically the correct corrosion allowance. A standard project value for minimum design metal temperature is not automatically conservative. You must understand the complete operating system. What happens during startup? What happens during shutdown? What happens if an outlet becomes blocked? What happens if a control valve fails open? Can higher upstream pressure reach the vessel? Can liquid become trapped and thermally expand? Can steam condense inside a closed vessel? Can rapid draining produce vacuum? Can fire exposure increase pressure? Can chemical reaction continue after feed isolation? Can cold depressurization reduce the metal temperature below the normal operating range? These are not exceptional questions. These are design questions. Design pressure must reflect the maximum credible pressure at the relevant location, including static liquid head where applicable. A vertical vessel containing a dense liquid can experience materially higher pressure at the bottom than at the top. If you simply apply the top pressure to the entire vessel, the lower shell may be underdesigned. Design temperature must reflect the metal temperature corresponding to the governing condition, not merely the process fluid temperature copied from a datasheet. Maximum temperature influences allowable stress, bolting, flange rating, material behavior, and heat treatment requirements. Minimum temperature influences toughness and brittle fracture risk. A vessel can be strong and still be brittle. You must ask what the lowest credible metal temperature is while significant stress exists. Depressurization, flashing, refrigeration, cold startup, gas expansion, and emergency shutdown can create low-temperature conditions that never appear during steady-state operation. Then consider vacuum. Vacuum is one of the most underestimated pressure vessel risks because engineers often say, the process does not normally operate under vacuum. That statement is irrelevant. The correct question is whether vacuum can occur during any credible operating, shutdown, cleaning, draining, cooling, maintenance, or failure condition. Internal pressure tends to expand a vessel. External pressure tries to collapse it. These are different structural problems. Internal pressure resistance is strongly influenced by strength and thickness. External pressure resistance is governed by stability, geometry, unsupported length, stiffness, and imperfections. A vessel can withstand substantial internal pressure and collapse under a relatively modest external differential pressure. Steam out followed by condensation can create vacuum. Draining without adequate venting can create vacuum. Cooling a closed vessel can create vacuum. Pumping liquid out faster than replacement gas enters can create vacuum. Utility failure can create vacuum. If vacuum is credible, design for it or establish reliable protection against it. Do not rely on habit, optimism, or an operator remembering to open a vent. External pressure calculations also make fabrication tolerances structurally important. Out of roundness is not a cosmetic defect when buckling resistance is involved. The calculation assumes a vessel geometry within defined limits. Inspection must confirm that the fabricated vessel still matches that assumption. Now look beyond pressure. A vessel experiences combinations of loads, not individual loads politely applied one at a time. It may carry internal pressure, self-weight, process liquid, internals, insulation, platforms, piping reactions, wind, earthquake, nozzle loads, thermal expansion, vibration, and relief discharge forces simultaneously. The hydrotest condition may govern the supports because a vessel designed to contain light gas can become several times heavier when filled with water. The empty condition may govern wind stability. Transportation may impose accelerations and support conditions that do not exist after installation. Lifting may create severe local loads through temporary lugs or trunnions. Software will calculate the load case you enter. It cannot warn you about the load case you forgot. Material selection demands the same discipline. Allowable stress is not a complete material selection criterion. The material must also suit the service temperature, required toughness, corrosion environment, welding process, fabrication route, heat treatment condition, inspection requirements, and intended operating life. A corrosion allowance can compensate for expected general metal loss. It cannot reliably protect against every degradation mechanism. Pitting, stress corrosion cracking, hydrogen damage, erosion, crevice corrosion, and corrosion under insulation do not behave like uniform thinning. Adding thickness may provide little protection against a cracking mechanism. Your corrosion philosophy must therefore be explicit. Are you relying on corrosion allowance, resistant material, cladding, weld overlay, lining, coating, inhibition, process control, inspection, or planned replacement? Usually the credible answer is a combination. You should also design the vessel so its condition can be understood later. If the regions most likely to deteriorate cannot be inspected, the design creates future uncertainty. That uncertainty eventually becomes risk, unnecessary replacement, or both. Then examine the openings. Every nozzle removes pressure-resisting material from the shell or head. Reinforcement restores capacity through excess shell thickness, excess nozzle neck thickness, added reinforcement, or integrally reinforced geometry. However, passing the pressure reinforcement calculation does not mean the nozzle is fully designed. The nozzle may also experience piping moments, thermal expansion, heavy valves, vibration, dynamic loads, or interaction with nearby openings. Pressure reinforcement and external load assessment are different questions. Large nozzles, bottom nozzles, agitator connections, closely spaced nozzle clusters, and connections near geometric discontinuities deserve early attention. Do not leave nozzle load compatibility until fabrication is advanced. The vessel designer needs piping loads, while the piping engineer needs nozzle allowables. If this interface is not deliberately managed, it becomes a late project loop involving rerouting, extra supports, local reinforcement, drawing revision, and commercial dispute. Freeze the major nozzle arrangement early. Treat every latent nozzle addition or relocation as an engineering change, not a drafting change. Welding also begins at the design stage. A weld is not merely a line joining two components. It changes the material locally through heat input, solidification, residual stress, heat-affected zone behavior, and distortion. Your material selection affects weldability. Your thickness affects preheat and heat treatment requirements. Your geometry determines access. Your joint detail influences examination. Your attachment arrangement can obstruct welding, inspection, or repair. A design that can be calculated but cannot be fabricated consistently is not a good design. Post-weld heat treatment must also be considered before fabrication begins. It affects sequence, dimensions, mechanical properties, examination timing, machining, repair planning, and schedule. A small attachment added after major heat treatment can create major complications. That is why clips, lugs, platforms, insulation supports, ladder attachments, earthing lugs, internal tray supports, and nameplate brackets should not be dismissed as secondary details. Every welded attachment to the pressure boundary deserves controlled engineering. Nondestructive examination is another area where terminology can replace thinking. Radiography, ultrasonics, magnetic particle examination, and liquid penetrant examination do not create quality. They detect particular types of discontinuities under defined conditions. The correct question is not simply, how much examination do we specify? The correct questions are, what defect are we trying to detect? Where would it occur? What orientation would it have? Which examination method is suitable? When should the examination be performed? What acceptance criteria apply? The assumed weld joint efficiency, weld configuration, examination extent, drawing notes, and inspection plan must tell the same story. If the calculation uses one efficiency while fabrication follows another examination basis, the vessel may be designed and built on inconsistent assumptions. Pressure testing is equally important, but it must not be treated as proof of infinite safety. A hydrotest demonstrates pressure integrity under a defined test condition. It does not prove vacuum resistance, fatigue life, corrosion resistance, relief capacity, nozzle load adequacy, or future service performance. Hydrotest planning must consider test pressure, test temperature, water quality, air removal, venting, temporary blinds, support loads, flange ratings, drying, and disposal. For sensitive materials or services, poor test water or inadequate drying can create new corrosion risks. Pneumatic testing requires even greater discipline because compressed gas stores far more recoverable energy. When pneumatic testing is necessary, it must be treated as a hazardous engineered operation, not as a convenient alternative to water filling. Pressure relief is not an accessory added after vessel design. It is part of the vessel protection system. The pressure boundary and the relief system must be engineered together. You must identify credible overpressure scenarios before sizing the relief device. Blocked outlet, control failure, fire, tube rupture, thermal expansion, loss of cooling, reaction, gas blowby, and wrong valve alignment can create completely different relieving requirements. A relief valve cannot protect against a scenario nobody identified. Even a correctly selected valve can be defeated by poor installation, excessive inlet pressure loss, back pressure, block discharge, incorrect isolation, wrong orientation, fouling, damaged rupture discs, or uncontrolled field modification. The relief path needs lifecycle ownership. Documentation also belongs to the integrity system. Material certificates, calculations, drawings, weld maps, heat treatment records, examination reports, repair records, test reports, nameplate information, and data reports define the engineering identity of the vessel. Without those records, future engineers cannot reliably inspect, repair, re-rate, or modify the equipment. Missing documentation turns future integrity decisions into assumptions. Do not treat final documentation as clerical closeout. It is the preserved memory of the pressure boundary. For disciplined engineers, your responsibility is technical ownership. You should be able to explain why the design pressure, temperature, minimum metal temperature, material corrosion allowance, examination, heat treatment, and relief basis were selected. For lead engineers, the responsibility is technical coherence. You must ensure the process datasheet, calculation, vessel drawing, nozzle schedule, piping loads, support loads, inspection plan, and vendor documentation describe the same vessel. For operations and maintenance engineers, the question is whether the vessel can be safely operated, isolated, drained, inspected, opened, repaired, and returned to service throughout its life. The most dangerous projects are not always those with weak calculations. They are projects where disciplines perform strong calculations from incompatible assumptions. So when you review your next pressure vessel, do not begin by asking whether the shell thickness passes. Ask what condition governs. Ask whether vacuum is possible. Ask what changes during startup and shutdown. Ask where the load enters the shell and where it goes. Ask what deterioration mechanism is credible. Ask whether the nozzle calculation includes the real piping loads. Ask whether the vessel can be fabricated, examined, tested, inspected, and maintained as intended. Ask what assumption could invalidate the entire design. The code provides rules. Engineering provides coherence. Pressure integrity exists only when process conditions, materials, structural design, welding, inspection, testing, relief protection, operation, and lifecycle management remain connected. Design the boundary correctly. Challenge every assumption. Build for inspection. Protect against credible failure. Preserve the engineering record. That is how you stop designing vessels that merely pass calculations and start designing pressure systems that survive reality. Share this podcast with engineers working in pressure vessel design, process plants, fabrication, inspection, reliability, and maintenance. Subscribe to the channel for more technically grounded engineering discussions. Follow my LinkedIn newsletter for deeper standards and recommended practices simplified editions, and leave your views in the comments. What is the most serious pressure vessel mistake you have encountered in a real project? Missed vacuum, wrong design pressure, corrosion, nozzle loads, welding, supports, relief protection, or uncontrolled modification. Your experience may prevent another engineer from repeating it.